Chemical equilibrium is important. It's all around us. So we're going to work on it some more. If, for example, where do you get the energy to breathe, lift a pencil? Well, it's through glycolysis. Pretty much every organism known to man involves glycolysis to get energy, to stay alive. And it's pretty much like a 10-step equilibrium process here. So what we're going to work on is predicting whether a system is at equilibrium or not, and then also determining equilibrium composition. So that probably means more ice calculations. Remember that? Determining equilibrium compositions. So a little review. With the symbol for the equilibrium constant being Kc, what does the C stand for again? Do you remember? Concentration. The one and only way to change any Kc, remember Kc is just a number, right? You divide the products, their concentrations, by the reactants, and everything's raised to the stoichiometric powers. You leave out solids and liquids, you get a number, and that number is Kc. And the only way to change that number is temperature. Okay. The equilibrium concentrations at 25 degrees Celsius for the below reaction are found to be. What is the value for Kc at this temperature? Now, don't get into the mode of wanting to do ice all the time, right? This isn't asking for what's the equilibrium composition. It's asking for what is Kc? Well, write an expression for Kc. Products over reactants. Calcium hydroxide has to be squared, divided by the calcium ion, and that's squared, and hydroxide concentration, that's cubed. So if we know these concentrations, we just plug and chug. And sure enough, they told us the concentrations. They're the equilibrium concentrations. We don't need to do ice. So products over reactants. Calcium hydroxide, 2.5 squared, all over calcium ion, 4 squared, hydroxide cubed, 2.5 cubed. So 2.5 squared divided by 4 squared divided by 2.5 cubed equals about 0.025. And no units on equilibrium constant expressions. Sorry, no units on equilibrium constants. That's a job for more advanced courses to see why. Two types of problems today. Here's the first type. How can you predict if a reaction is at equilibrium? So they're going to give you all the amounts of everything, and you predict if it's at equilibrium or not. And if it's not, will more reactants or products form in order to finally reach equilibrium? How do you do it? Calculate a QC. What's a QC? It's a reaction quotient. And remember, Kc was just products over reactants. Their concentrations raised to their stoichiometric powers, right? Well, that's how we calculate Kc. So what we're going to do is we don't know if we're at equilibrium or not. We're given all these amounts of products and reactants. Just erase Kc and write Qc. We're going to calculate this Qc. Calculate a number. It's just going to be a number. Okay? So when we get that number, there's 3 possibilities for it, for that number. That number we get could be bigger than our equilibrium constant. Right? It could be smaller than our equilibrium constant, or it could equal our equilibrium constant. So let's take a look at the first scenario. This reaction quotient, we calculate products over reactants. It's too big. It's much bigger than Kc. That means there's too much, right, product, because our number is too big, right? And Kc and Qc, they're both products over reactants. So if Qc is too big, that means we have too much product. We have too much product. And the reaction must shift, right? Reactants, products, Reaction, we have too much product, so we have to shift towards reactants. When QC is smaller than KC, that means there's now too much reactant, right? The number's too small. So we're dividing by too big of a number. We have too much reactant. So now it has to shift to form products. We do the math, and we get QC to match KC. Then we're at equilibrium. That's the only time you're at equilibrium. So we found KC in the last example to be 0.025. Okay. However, what if these were the concentrations? Are you at equilibrium? So is the system at equilibrium? They're giving us the concentrations. This is not an ice problem. They're just saying, are you at equilibrium? So calculate a QC. Products over reactants, right? So it will be the concentration of calcium hydroxide squared. So that'll be 13.4 squared divided by the reactants to their stoichiometric powers. Calcium squared, so here's calcium, 2.6 squared, hydroxide cubed, 8.9 cubed. What do I get? I get 13.4 squared divided by 2.6 squared divided by 8.9 cubed, about 0.0376. Okay. Did I get KC? No, I didn't. This is 0.0376. So, are you at equilibrium? Definitely not. Which direction will it shift? QC is greater than KC, right? QC is too big. And remember these expressions, they're always products over reactants. Always. So if it's too big, that means I have too much product. I have too much product. So if I have reactants and products, and if I have too much product, it has to shift in that direction and give me more reactants. Those products, those excess products have to react. Okay? So you can say, just draw your arrow or say shift to the left. The second type of problem. Now we're given KC number, so that means we're given the number for the equilibrium constant, and we're given the reaction. How can the equilibrium composition be found? Okay, now does this sound familiar? Find the equilibrium composition. That means you're going to have to do ice. Do ice. But since we're using a KC, mole tables won't cut it. We have to make a concentration table in our ice table. Then we're going to solve for x by substituting into the KC expression, and we'll have all of our answers. Let's try it. In a 1 liter vessel, 3 moles of chlorine, 5 moles of bromine are mixed. The equilibrium constant is 50. What are the final equilibrium concentrations? So they're asking for this composition. Definitely an ice problem, okay? And it has to be a concentration table, okay? Whenever they give you KC, has to be a concentration table. So the initials, but it has to be in concentration. So chlorine is 3 moles, 3 moles over 1 liter. Bromine is 5 moles over 1 liter. And we don't have any bromine chloride. Changes, minus for reactants, positive for products. So we'll have 3 minus x for chlorine, 5 minus x for bromine, and just 2x for the bromine chloride. Okay? Kc is 50. So we made our concentration table. Now let's solve for x by substituting in the Kc expression. The next part. Kc, so we don't screw up, I'm just going to write the expression first. Bromine chloride squared all over chlorine concentration and bromine concentration. Okay, so they said Kc is 50. So 50 has to equal bromine chloride, and it has to be squared. And remember, these are all of our answers. So that's what we have to put in there. That's 2x, and it has to be squared. Chlorine is 3 minus x. Bromine is 5 minus x. Okay? We need to solve for x. This is not going to be pretty, is it? Okay. So let's 50. It's going to be, well, 4x squared up on top, right? Let's multiply through our bottom. We're going to have 15, multiply through by 3, 15 minus 3x, multiply through by the negative x, minus 5x plus x squared. Okay. Let's bring that to the top, right, with the 50. Bring along the diagonal. So we have to multiply it through by 50 then. 50 times all this stuff. So 50 times 15 is 750 minus 50 times a negative 3 is 150 x minus 250 x plus 50x squared has to equal 4x squared. Follow me so far? So all I did is I brought the purple parentheses up to the top with the 50 and multiplied through by 50. Okay, I can combine these two. I'll have 750 minus 400x plus 50x squared equals 4x squared. Now I need to get things in that form of the quadratic formula. Do you remember that? The quadratic formula looks like this. ax squared plus bx plus c equals 0. And I'll have negative b as solutions, plus or minus the square root b squared minus 4ac all over 2a. So I need to get my a, b's, and c's. So let's bring the 4x squared over to the other side, and I'll have 46x squared minus 400x plus 750 equals 0. Now you can divide through by 46 or just use these numbers. I just use these. Why not? We have calculators, so there's my A, there's my B, and there's my C. So I'll have negative B, plug that stuff in then, negative B, negative 400, well, B is a negative 400, negative is a positive, so I'll have 400 plus or minus square root negative 400 squared minus 4 times 46 times C 750 divided by 2 times 46. So 400, let's see, 400 squared minus 4 times 46 times 750, hit equals, take the square root, I get about 148.3. So I have 400 plus or minus 148.3 divided by 2 times 46, 92. Okay, so my x has two possibilities here. Let's find the first one. 400 plus 148.3 equals, divide by 92 equals about 5.96. That's one possibility. Now let's do the other one. 400 minus 148.3, it equals, divide by 92, you get 2.74. Okay, so my answers, they're getting really close now. One of those isn't going to make sense. So chlorine is 3 minus x. What else? Bromine is 5 minus x. And BrCl is 2x. There's my answers. Okay, so which one doesn't make sense? If I take x to be 5.96, I get a negative answer right here. So that means this won't work, because I can't have negative answers. Okay, so that means this one must be it. So x has to be 2.74. So 3 minus 2.74 is about 0.26. 5 minus 2.74 is about 2.26. And 2 times 2.74 is about 5.48. Okay, and these are, remember the units? Kind of left them off here, but these are concentration tables. So everything is big M. That's how it's always going to be, because you have to make a concentration table. Molar bromine and molar BrCl. Solely on the basis of the value of Kc. So just looking at the number, decide whether or not you expect nearly complete reaction at equilibrium for the following reaction. So all they're saying is it's a conceptual question. Kc, remember, is products over reactants. And if they say nearly complete, that means, man, it's completely going in this direction, your equilibrium constant expression. There's hardly any backwards reaction at all. This is going to be a huge reaction. You have hardly any backwards reaction. There's hardly any reactant left. So that would be nearly complete reaction, means huge, huge equilibrium constants. Wow, this is extremely small, 10 to the negative 31. So no way. No, you do not expect a nearly complete reaction. The reaction hardly starts and it's over. Okay. If the concentration of nitrogen and oxygen both equal 4.5 times 10 to the negative 4.5 times 10 to the third, what will be the equilibrium concentration of NO2? Is this an ice problem? It's not, because they're not asking for the composition. You don't need to find the concentration of everything. You just need to find the concentration of one. So how could you do this? Set it up the Kc expression. Kc is products over reactants. NO2 all over nitrogen, and oxygen has to be squared. Okay? We know nitrogens, we know oxygens, we know Kc, and solve for it. Right? We know everything. Just solve for the unknown. So Kc is 4.6 times 10 to the negative 31. That has to equal NO2, is what we're trying to solve for, divided by nitrogen, which is 4.5 times 10 to the third. divided by oxygen. I forgot to square it, right? Because that should be a 2 there. Shouldn't that be a 2 there? So it has to be oxygen squared. 4.5 times 10 to the third, but squared. So solve for NO2. The equilibrium constant Kc for the reaction phosphorus trichloride plus chlorine gas forms phosphorus pentachloride is 49 at 230 degrees Celsius. If 0.4 moles each of phosphorus trichloride and chlorine are added to a 4-liter reaction vessel, what is the equilibrium composition of the reaction mixture at 230 degrees Celsius? Equilibrium composition definitely means do ice. Okay, so we're going to make a concentration table, an concentration ice table, substitute into the Kc expression, solve for x, and then get your answers. Okay? Phosphorus trichloride plus chlorine forms phosphorus pentachloride. Ice. Initial concentration, change, equilibrium concentrations. Initial, we have 0.4 moles all over 4 liters. And that's the same for both. And we don't have any phosphorus pentachloride. Change, minus x for reactants, plus x products. So we'll have 0.1 minus x, 0.1 minus x, and x. Okay, let's substitute into our Kc expression. Products over reactants. Phosphorus pentachloride all over phosphorus trichloride and chlorine. So Kc is 49. So 49 has to equal phosphorus pentachloride, which is x, divided by phosphorus trichloride, which is 0.1 minus x, and the same for the chlorine. Okay, so let's solve for this x. Let's see, let's multiply the bottom one through first. 0.1 times 0.1, it's just 0.01, right? 0.01. So we'll have a negative 0.1x, and then, right, and then multiply the next one, negative 0.1x plus x squared. Bring this up to the top with the 49, okay? So we'll have 49 times 0.01, it's just 0.49, 0.49, and negative 4.9x, negative 4.9x plus 49x squared equals x. Okay? So 4.9 is 9.8. So I have 0.49 minus 9.8x plus 49x squared equals x. Bring the x over to the other side and rearrange. I'll have 49x squared minus 10.8x plus 0.49 equals 0. Okay, now I can substitute into my quadratic expression, right? Remember, that's just negative b plus or minus the square root b squared minus 4ac all over 2a. So there's my A, there's my B, there's my C. So I have a negative, well, negative and negative is a positive, so let's just make that positive 10.8 plus or minus a negative 10.8 squared minus 4 times 49 times 0.49 all over 2a. So what's that going to equal? That's going to equal 10.8 plus or minus, okay, 10.8 squared minus 4 times 49 times 0.49, hit equals square root of 4.54 all over 49 times 2, which is 98. Okay, so that means my x has two possibilities here. 10.8 plus 4.54, hit equals, divide by 98, could be 0.157. Or x could be 10.8 minus 4.54 equals, divided by 98, 0.064. So one of those numbers is not going to make sense. Let's see if we can figure out which one it's going to be. I'll go, what are my answers here? Here's my answers. So PCl3 is 0.1 minus x. Concentration of PCl3 is 0.1 minus x. The concentration of chlorine is 0.1 minus x. And the concentration of phosphorus pentachloride is x. Okay. Which one doesn't make sense? It can't be that one. It's too big. It'll give you negative answers. So that means it must, x has to be 0.064. So this has to be 0.064. So 0.1 minus 0.064 is 0.036. There's my equilibrium answers. Calculate the composition of the gaseous mixture obtained when 1.25 moles of carbon dioxide is exposed to hot carbon at 800 degrees Celsius in a 1.25 liter vessel. The equilibrium constant is 14. Okay, again, composition. So let's do ice. Let's make a concentration table. Then we'll substitute in our Kc expression and solve for x. And then we'll get our answers. So we have moles over liters. So 1.25 divided by 1.25 is just 1. Okay. Carbon, it's a solid. It doesn't show up. Right? So just draw dashes all the way down. Carbon monoxide, there's none of it there initially. Okay. So the change row, minus x, 2x. So we'll have 1 minus x and 2x. Okay, so now we're ready to substitute into our Kc expression. See if we can solve for x. Kc is products over reactants. Carbon monoxide squared divided by carbon dioxide. The 1 power. Okay, carbon solid doesn't show up, remember? So that means I'm going to have, what is it? Kc is 14. So 14 has to equal CO squared. That's 2x quantity squared divided by carbon dioxide, 1 minus x. Okay, let's bring the 1 minus x up to the top. So I'll have 14 minus 14x has to equal 2x quantity squared is 4x squared. So let's rearrange and get it into our quadratic formula. Let 0 equals 4x squared plus 14x minus 14. So now we're ready to substitute into our quadratic formula. Negative b plus or minus the square root b squared minus 4ac all over 2a. Negative b, negative 14 plus or minus the square root b squared, 14 squared, minus 4ac divided by 2a. Okay? What is that going to be? 14 squared minus 4 times 4 times 14 negative equals square root 20.5. So my two possible answers for x. Okay, so we'll have two possible answers for our x. X could be two possible answers. 14 negative plus 20.5 equals, divided by 8, about 0.8125. Then the other one, 14 negative minus 20.5 equals, divide by 8, negative 4.3. Okay, which one doesn't make sense? Let's take a look at our answers here. CO2 is 1 minus x. Concentration of CO2 is 1 minus x. Concentration of CO is 2x. Okay, so I think it's kind of obvious which one won't work. Can't have negative answers, right? So our x must be 0.8125. So 1 minus 0.8125 is 0.1875. And 2 times 0.8125 is 1.625. Okay. So the game plan on these problems is pretty much like before. Make an ice table, but it needs to be a concentration table. Substitute everything into your Kc expression and solve for x. And then go back to your ice table, and now that you know what x is, you know what the equilibrium composition is.